Chapter 2, Part 2, Position Time Graphs. I really like this website, and so we're going to go to our browser window. They have an excellent discussion of position time graphs with way better graphics than I could create. So let's look at this. This is a motion diagram, actually. Ball rolling across a level table. Times are equivalent, 0.1 second, 0.2, 0.3, 0.4, so that the time interval between each is a tenth of a second. And the position of the ball shows us that it must be traveling with a constant velocity. If the distance traveled in this tenth of a second is the same as in this tenth of a second, and here, then the velocity is constant as it's traveling. So this is a motion diagram. Another way to show motion is with graphs, and the simplest graph of motion is our position time graph. Now this does not mean it's the x-axis. It means that the position is horizontal, and horizontal is x, just like vertical is y. And so yes, we will put an x value on what we think of as our y-axis. Time will always be our independent variable and will always be on what we call our x-axis. So the horizontal axis is time, and the vertical axis is position, which often is referenced with the letter x. So this is a position time graph of this motion. At 0.1 seconds, the ball was at 20 centimeters. At 0.2, it was at 40. At 0.3, it was at 60. And at 0.4, it was at 80 centimeters. I think I might have said seconds before. These are centimeters. These are seconds. The slope of a position time graph will give us the average velocity of the object as it's moving. Now, this is also a constant velocity. It's a perfectly straight line. But even if the line were a little bit curvy, if you find the average slope by simply taking the change in y, okay, this says change in x because it's position and that's what's changing, okay? It's the change in the vertical axis divided by the change in the horizontal axis. So if I take 20 centimeters, which is the change in the vertical axis, and divide it by 0.1 seconds, the change in the horizontal axis, I get 200 centimeters per second. So right here, that's the average speed. By definition, you might want to write this down, by definition, the average velocity is the slope of the position time graph. Pay attention to your units. This graph was graphed with a position unit of centimeters and a time unit of seconds, and so the velocity units are centimeters per second. Also notice that this was a positive slope. Because the slope was positive, the velocity was positive. That means the object was moving in a positive direction. Some other shapes that you might see. What does a horizontal line on a position time graph tell you? Well, remember, this is position. And if the position's not changing, well, the object is standing still. So a horizontal part of a position time graph means that the velocity is 0. It means the object is not moving. This is a positive slope. A positive slope would tell you that the object had a positive velocity, that it is moving in a positive direction. Okay, look at this graph. Here's our time axis. So this is positive position, and this is negative position. Okay, so this graph goes all the way down to here. So if we look at the motion, it starts in a negative place. It moves its position getting less and less and less negative as it moves to 0. The slope is positive. So this object, while it is in a negative space, it has a positive velocity because the slope is positive. This is a negative slope. That doesn't tell us it's slowing down. It's actually, it's a straight line, so the velocity is constant. But the slope is negative, that means the velocity is negative. So in this person's website, they talk about South Clyde Morris Boulevard and the International Speedway. They're in Florida. We're in Savannah. So in the class, I might talk about Washington Avenue, and moving east along Washington Avenue as being positive, and moving west along Washington Avenue would be moving negatively. So this would be moving west along Washington Avenue. Let's say this is the school And then maybe this is Habersham. And so the object is moving away from the school, moving more negatively towards Habersham. So it's a negative velocity. It doesn't tell you how fast. Actually, if you found the slope, it would tell you how fast. But the fact that it's negative is direction, okay? Positive direction, negative direction. This object is in a negative space, moving negatively. So if we wanted, let's say Washington and Paulson to be our origin, then anything west of Washington and Paulson would be negative. So this car would be moving from Paulson toward Habersham in a negative area, moving in a negative direction. Okay? So slope tells you the direction. Steepness of slope tells you how fast. So a steeper line tells you faster, that the object's moving faster than a less steep line. This line is steeper than that one. They're both positive. This object is moving faster than that object. So let's do a little exercise here. Here's a graph. It's a position time graph. Here's the origin. This is in a positive area. This is in a negative area. During which intervals is the object traveling in a positive direction? Remember, direction is gotten by the slope of the line. And if it's moving in a positive direction, the slope is positive. And if it's moving in a negative direction, the slope is negative. So there's no slope here, but here is an area of positive slope. So the object is moving in a positive direction here. No slope again. Well, here's a positive slope. So these two time intervals from 2 seconds up to 5 seconds, it's moving positively, and then from 6 seconds up to 7 seconds, it's moving positively. During which intervals was he traveling in a negative direction? Direction is gotten by looking at the sign of the slope. So what we're looking for here is a negative slope. Well, I only see one on this whole graph, and it happens from, let's see, 5, 6, 7, 8, 9, all the way through 11. Okay, so from the 9th second through the 11th second, there's a negative slope, and so the object is moving in a negative direction. During which interval was he resting in a negative location? Well, there are two resting places. There's here, and there's here. Here, he's resting at the origin, which is not a negative location, but here, he's resting at -2. So resting in a negative location happens between 0 and 2 seconds. Resting in a positive location, this is not positive, 0. This is positive. So from the 7th second to the 9th second, resting in a positive position. During which two intervals did he travel at the same speed? We're looking for the slope here, not the sign of the slope, but the slope. It's the magnitude of the slope. And if you look at this interval and this interval, the velocities are opposite, but look at the distance traveled in time. Here's 1 second, traveling 3 meters. Here's 1 second, traveling 3 meters. Actually, 2 seconds, traveling 6 meters. So the speed would be the same here and here. 3 meters per second would be the speed here and the speed here. Different directions, but the same speed. Average velocity, remember, is the slope of the position time graph. Average velocity can be found by dividing the change in position by the change in time. On a position time graph, this is the slope, the change in the vertical axis divided by the change in the horizontal axis. The instantaneous velocity is the velocity at an instant, velocity, in a very, very small bit of time. So your speedometer on your car would measure instantaneous velocity. It does not measure average velocity. If you want to know your average velocity, you'd have to measure a certain distance and time and divide them. Perhaps you have a button on your car that would tell you what the average velocity for the last period of time is. But instantaneous is what your speedometer tells you. How is speed different? Speed is the the absolute value of the slope of a position time graph. Okay, so it's the steepness, not regarding positive or negative, just how steep it is. Speed is just how fast, not in what direction, just how fast. Reviewing a little, how did we show different velocities on a motion diagram? It was the distance between the dots. So if something's moving slow, the dots are close together. If it speeds up, the dots get farther apart. And then we can have it slow down again. So fast, slow, and slow again. How do we show different velocities on a position time graph? Well, the steepness, if it's going really fast, the steepness of the graph will be higher. So this one's faster, and this one's slower. And this one, I'm going to make it a different color. This one is moving in a negative direction.